Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my titanium physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! Far, far above, time standing still, memories are one, same space, same will, now move along, light speed divides, rips all from one, it blows my eye holes and fills me with real power, fills me with real power, 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 power. Everything has edges. Points past which we don't understand. Desks have edges, lives have edges, even a mathematical understanding of the universe has edges. These edges in physics often show up as infinity. A point, for instance, where the energy density becomes infinite. A point where we definitely don't know what's going on. And we call these points singularities. Before we go on, the word singularity is a misleading one. A single of something is just one unit, after all. A single serving of bread, a single serving of cheese, a single serving of disappointment. But the word singular, in this case, doesn't refer to the quantity. It refers to the singular uniqueness of the point. It's a point where our theories stop applying. The singularities represent the edge of our understanding. Today on the Titanium Physicist Podcast, we're talking about singularities. Speaking about the edge of understanding, today's guest is an expert at the boundary. He's an American artist, composer, and director, and he's the writer and artist on the show Adventure Time, and is responsible for some of my favorite episodes, including the episodes Wizards Only Fools and The Great Birdman. He's also the author of a crazy awesome webcomic called Forming, and Forming Volume 2 is coming out in stores this spring. Welcome to my show, Jesse Moynihan.
Thanks, man.
Oh, man, I'm so excited to have you on. This is going to be fun.
I'm glad that song resonated with you. Okay, good.
So Jesse, for you today, I've assembled two of the best titanium physicists in the world. Arise, Dr. Jocelyn Read!
Rawr!
Dr. Jocelyn did her undergraduate at UBC, her PhD at University of Wisconsin-Milwaukee, and she's currently faculty in the physics department at Cal State Fullerton. She's a specialist in neutron stars. Now arise, Dr. Katie Mack.
Ta-da.
Dr. Katie did her PhD at Princeton University in astrophysical sciences. She's currently at the University of Melbourne in Australia, where she's a postdoc and a Discovery Early Career Research Award holder. She studies theoretical cosmology. All right, everybody, let's talk about singularities.
Okay, the first thing we wanted to do was say the word singularity gets used a lot in different places, and sometimes it's used sort of haphazardly, but it's got kind of a mathematical meaning, which is that things blow up. But we mean this in a precise way, right? So one of the simplest things is if you think about what happens if you just try and look at the function 1 over x. When x is 2, it's a half. When x is 4, it's a quarter. As x gets bigger, it gets smaller. But the opposite happens as x gets smaller. So at a half, 1 over x is 2. And at a quarter, 1 over x is 4. And then as you get closer and closer to 0, it gets bigger and bigger to infinity. So at 0 is a singularity. We say it's not defined precisely, it blows up. And we can handle that in math. The idea is people have often thought if your physical theory of the universe has a singularity in it, then something's going wrong.
Does that have to do with that paradox where you walk halfway to a wall?
Yeah, that's a great example. Let me rephrase what Jocelyn said. Those are Zeno's paradoxes, right?
Yes, Zeno's paradox.
Yeah. So Zeno's paradox was all about motion.
Okay.
Philosophically, Zeno didn't think that anything changed because to change something, you'd have to change it a little bit. And to change that a little bit, you'd have to change it an even smaller amount. And he was against the whole idea. And so he came up with these paradoxes. And Isaac Newton took Zeno's paradoxes and he turned them into math and then he crushed them. But the deal is Zeno's paradox is a wonderful example. I want you to imagine that you're on the periphery of a big circle. On the street, somebody's drawn a big circle. So they put an X right in the middle and you stand on the edge. And the game goes like this. Yeah. Every time you go halfway between where you're currently standing and the center of the circle, you get a cookie. Right. You walk halfway to the center of the circle, and then the guy next to you gives you a cookie. And then you walk another halfway, but this other halfway is a quarter of the distance to the center. And then you get another cookie. And then you go an eighth distance to the center, and then you get another cookie. And then you go 1/16th to the distance to the center, and you get another cookie.
Yeah.
Okay, so how many cookies do you get by the time you get to the middle of the circle?
Like infinity cookies.
You get yeah. That's what we mean by the singularities. So this is essentially what Jocelyn was describing.
The neat thing about singularities is some things are perfectly well described. Like, we can measure lengths to the center of the circle and be totally happy talking about them. And then other things that depend on that length behave in weird ways, like giving you infinite cookies. So a lot of this is trying to reconcile the things that behave in ways that are easy to understand with the things that don't. And I mean, length, it turns out, even though Zeno was like, we'll never get to the center, it turns out that you can take effectively an infinite number of infinitely tiny steps in a finite time. So that turns out not to be a problem because of calculus, basically. But other things don't go away with calculus. So there are singularities that remain even when we do all the tricks.
Okay. I mean, Zeno's paradox is kind of resolved. You play the same cookie game. And this time, the first time you go halfway to the center of the cookie, he gives you half a cookie. And then the next step, when you go, a quarter to the center, he gives you a quarter of the cookie. And then as you go to an eighth to the center, he gives you an eighth of the cookie. And so the process of him giving you cookies, he'll do it an infinite number of times. By the time you reach the center of the cookie, you only have one cookie instead of an infinite number of cookies.
I understand what you're talking about, but I also feel like there's this other, say in the Big Bang, right? Mm-hmm. When everything started from this single unit.
Yeah.
And then exploded into infinite space-time. So that action, the Big Bang action, so everything before we formed into, and this has to do with that Zergiak song, before we formed into individual pieces, like definable matter, I guess, or whatever.
Yeah.
When we exploded from that single point, everything was the same energy junk, right?
Yeah. I mean, there's a precise way that our model of the universe has a singularity. And it's a similar idea, except now if you try and go back in time and you look earlier and earlier, everything gets closer and closer together.
Yeah.
Until at sort of a finite time ago, at the Big Bang, the start of the universe, the entire universe was all together in a single point.
So that singularity, the Big Bang singularity, means you can't look beyond the beginning of the universe, farther back, because space-time comes into being at that singularity, if that's the model you're using. But we also can't see the singularity. I mean, we can't go back to that point with our physical models either, because quantum gravity becomes important when you get to things being dense enough that you're at this stage where we can't just use gravity and quantum mechanics as separate things anymore. Everything's so dense and so packed close together, and such high energy densities that you need to have a unification of quantum mechanics and gravity, and we don't have that at the moment. So even before you reach the singularity, we still can't deal with that with, sort of our current understanding of physics.
Right.
Let's get back to singularities, because you were talking about the Big Bang, and the Big Bang singularity is actually fascinating.
Yeah.
But to understand it, you have to kind of understand singularities at the hearts of black holes, because they're very similar things.
Yeah, so black hole singularities are an inevitable consequence of gravitational collapse. So what happens is you have a star, and normally a star is kind of held up by the nuclear reactions happening inside the star. So you have a whole bunch of material, and you're creating nuclear reactions in the center, and that's burning usually hydrogen into helium or something, and that's creating a pressure that pushes the outer bits of the star out and keeps it in this sort of vaguely spherical shape. And so the star has a lot of gravity that's pulling it in, and then it has this pressure that's pushing it out, and so it's in equilibrium, it's stable. And what happens with a star is that eventually the star runs out of fuel, and various things happen with like blowing off layers and supernovae and stuff like that. But at some point you get to a point where you don't have any more fuel to push the layers out, and you have nothing to keep the star from collapsing under its own gravity. And there are a number of phases that you go through with different kinds of, exotic matter that have different kinds of pressure that can keep the star up for a while. But at some point you have so much matter in such a small space because you've run out of processes that can hold it up, and then the collapse becomes inevitable. And there are no physical processes that can keep this from happening. And when that happens, the star collapses in upon itself, and the gravitational field becomes more and more intense at the center, and you have this process by which you're basically sort of warping space-time by having so much gravity in one place. And that's what creates a black hole. So anytime you have matter in space-time, then that matter is creating a gravitational field, and that gravitational field can be thought of as curvature of space-time. So the more mass something has, the more strongly it's curving space-time, or the more dense something is, the more strongly it's curving space-time. And so black holes are when you have something that's curving space-time so much that it's basically becoming infinitely curved at the center. And that's the singularity. Okay. And the defining feature of a black hole, I guess, is the event horizon, which you might have heard of, which is where the curvature of space-time becomes so intense at the event horizon that light can't escape out of the black hole. So people talk about it as the place where the escape velocity, the speed at which you would need to be going to escape from that gravitational field, is higher than the speed of light.
And so one of the things about this collapse story turns out to be that if you have your collapsing star and it's just getting denser and denser and more concentrated, and if it falls so that all the mass is past the horizon, there's nothing left that can keep it from going to the very central point. Everything is just going to keep falling. Stars can have different properties and structures and things, but a black hole is just all the matter, every kind of stuff is all just at one point in the middle of it.
And in a sense, you still have the same amount of mass if you're looking at it from far away, but basically all that matter is sort of converted into space-time curvature because it doesn't have any properties anymore. It's just become this kind of space-time funnel, and all it's doing is collapsing into the center and making this sort of pinch in space-time where the curvature of space-time is really high, and it all goes to this central point, the singularity.
Okay, so there's two things that I want to emphasize about the collapse into a black hole that are actually pretty neat. And the first is, it's a type of runaway collapse. An example of runaway effects are kind of like greenhouse gas. People talk about it being a runaway thing, like global warming. The idea that things get out of hand. The more it warms, the more CO2 emitting things will happen, and the faster it will warm, and the faster warming will cause more CO2s, back and forth, right?
Yeah.
So what happens is, let's imagine yourself on the moon, okay? And imagine that I've made a machine that can stretch or shrink the moon's radius to any size I want, right? So I can make the moon really wide, I can make it really small, but the mass has to stay the same.
Okay.
So gravity depends on the distance from the center, and it also depends on the total mass. And so if I doubled the mass, that would double the amount of force that you feel towards the center.
So you'd notice that you'd weigh twice as much.
Yeah. But if I halved the distance, if I halved the radius of the planet, if I shrunk the moon down to a half its width, then you would, on the surface of the planet, feel 4 times as much force pushing you towards the center.
Okay. Yeah.
So shrinking down is a very effective way on making this force stronger and stronger and stronger.
Wait. So shrinking down and the mass stays the same?
Yeah. So even though the masses are the same, you're much closer to the center of mass if you shrunk down the object to a smaller size. And so gravity's stronger.
You're making it denser and more concentrated.
It's kind of like, the Earth. People go up into space. If you're really far away from the Earth in space, the gravity pulling you towards the Earth decreases, the force of gravity, right? And the closer you get to the surface of the Earth, the stronger gravity you feel. Yeah. So the same thing happens in this collapsing object, right? So you imagine you're standing on the surface of the stars, it's shrinking. As it's shrinking, the force causing it to contract is increasing dramatically.
Yeah.
And so the acceleration ramps up. Once the radius of the object is smaller than the event horizon, things become unreal. In terms of our regular intuition, the force pulling it together becomes unreal to the point that nothing can stop it from crunching down to a point.
Right.
So effectively, it kind of fights its way down to the size of the event horizon. Once it's under the event horizon, there's nothing that can stop it. It just goes down to a point. Accelerating collapse. Because the smaller it gets, the denser it gets, and the denser it gets, the stronger the forces are going to get. Okay, so there was a second thing I wanted to emphasize here with this black hole. It has to do with kind of the nature of the black hole. The idea is, if you look at a model of a black hole, everywhere you go in it, there's no matter. You feel the force of gravity kind of pulling you towards the center of the system. But if you had a big net, you could wave the net anywhere you want, and it wouldn't scoop up anything. Even if you fell inside the black hole, you still wouldn't scoop anything. It's a vacuum solution. Everywhere you go, there's nothing except for, at the very center, there's this place where the curvature is infinite. And so, but it's just one point. In fact, you can't even talk about it at a point. It's kind of like a time. Because everything on the inside of the black hole is going to hit it, it's more like an inevitability in time than it is of a location and place. Your question, why do we think that our theories can get to the point where we would say, yes, this place or time, this inevitability of this crunchy singularity at the center of the black hole will definitely happen? It's an interesting question because there was a time when we didn't think that it was going to happen. Okay. Jocelyn mentioned that the theories, when they first came out with this black hole model, everybody was like, no, this can't work because it's full of singularities. Because there's a second type of singularity that happens at a wider radius that happens at the event horizon. Okay. Something crazy happens at the event horizon. We keep saying the event horizon of a black hole, time can't escape. That does something totally bananas to the mathematics of the thing. And so everybody, when they originally came up with it, said, you know what? Stuff's probably going to come in and hit the event horizon, and there's a singularity there, and then it's going to disappear or something. Who cares what happens on the inside? That event horizon has a singularity too. Yeah. But it was an interesting example of why people need to be really careful with singularities. And it's interesting because the deal is that sometimes singularities show up in the mathematics, and they're not actual real singularities. It's just an artifact of the mathematics.
So you've seen this if you've ever looked at a globe.
Yeah. Okay, so we can talk about the latitude and longitude, right? Okay. So latitude is the height away from the equator, and then longitude is the distance around, like, clockwise around the world, right? Right. So you can talk about traveling a distance with a constant latitude, but a changing longitude, right? You're essentially staying at the same distance away from the equator, moving around the world, right? This system kind of breaks down when you're at the North Pole.
And the South Pole.
And the South Pole, yeah, there's two of them on the world, right? So when you're at the North Pole, you have a latitude, right? It's at the North Pole. What's your longitude? And the deal is that you're every longitude at once, right?
So you could say, like, I'm going along all these longitudes and I'm not actually traveling. It's a sort of a form of singularity. But the problem is with your coordinates.
Right. Yeah. Or you could think about you're increasing your latitude, and then at some point you can't increase your latitude because every direction you go is decreasing your latitude. And so it's like, where have you gone? You know, like, where do you go from there?
It's just a math problem. It's not a physical problem.
Yeah, right.
Yeah.
And so in general relativity, in this type of physics, it's very mathematical. And so it's really difficult because the singularity that happens at the event horizon of a black hole, it's called a traversable singularity. It's like the North Pole. So there's nothing strange about the North Pole. You can go to the North Pole and you can wander around it, and you, like, maybe if you take out a sextant, you might feel like, and measure the stars, you might be like, oh, things are weird here. But just in everyday usage, there's nothing strange about the North Pole. Very cold, but, you know, polar bears, fine.
And it took people about 20 years to figure out which of the singularities in the black hole were just because it's hard to talk about the coordinates and which were real physical singularities.
Yeah.
So the deal is originally they thought that maybe everything would crush up against the event horizon, but it turns out everything just passes through it.
Okay.
But then the runaway collapse is the reason we know that there's got to be something crazy going on right in the middle of the black hole. Right at the singularity, because you can't resist it. There's no way once it's inside the event horizon for the collapsing star to stop at some radius. In fact, its collapse is a matter of time instead of space. It's kind of like there aren't any rockets that we can use that can keep today from turning into tomorrow. There's no rockets you can use to keep, no matter how the rocket pushes, you can't hold a second still. And once you're inside the black hole, because it's a mathematical thing, but this inevitable crush is so strong that staying at a constant radius is exactly the same as trying to stay at 10 o'clock p.m., which is crazy. Runaway collapse. The point is, we're pretty sure, at least in canonical general relativity, this type of physics that Einstein invented, that everything in the black hole is just at the center. There's nothing anywhere else. Once you're inside the event horizon, you fall right down to the middle.
Okay. What's in there? Like, if it's sucking all this matter inside of it, right? And then it just gets crushed and chills in there.
The matter kind of ceases to exist as a physical thing. It turns into pure space-time curvature. It doesn't have properties anymore. It doesn't have atomic structure. That all gets crushed. It doesn't have a color or anything like that. It goes into the singularity, and then it's hard to define.
Yeah, mathematically, the singularity is literally the end of the universe.
This is also what we take now as a hint that our description breaks down right at the densest point.
Oh, yeah. Okay, so Stephen Hawking. You know who Stephen Hawking is, right?
Sure, yeah.
So Stephen Hawking is everybody knows his name and thinks he's a great guy. And the reason everybody knows his name and thinks he's a great guy isn't because of all those books he wrote. And it's not because he's in a wheelchair, although that's part of the reason he's fantastic. The reason everybody knows his name is in the 60s, he came up with a mathematical proof showing that general relativity, our physical model of gravity, is inconsistent at the singularity. So literally, somewhere on the singularity, our laws of physics can't be consistent. They have to break down.
Yeah. Do they break down into a new set of laws, or do they break down into just gobbledygook?
Well, they're inconsistent. All we know is that they're inconsistent.
So our philosophy is that there should be a new set of laws there. But this is more of an aesthetic faith that we can describe the universe in a consistent way. And we don't know the description right now.
Yeah.
It's a mystery.
It's kind of like when I was saying that at the Big Bang singularity, before you even get to the singularity, looking back in time, you get to a point where you have to deal with quantum mechanics and gravity working together. And we don't know how to do that. The same way we don't know how to reconcile the physics at the black hole singularity.
Yeah.
So the deal is, now that we've talked about the black hole singularity, now we can start talking about the Big Bang singularity, because their stories are very similar.
Mm-hmm.
So we know that the universe is expanding. We can measure that expansion, and we know that it's been expanding for a long time. And if you kind of dial that back in time, then things must have been closer together. And if you dial that back farther and farther in time, you get that at some point, basically everything would have been at a single point. And we know that we can't really, within our understanding of the physical laws, we can't really extrapolate back that far, because you get to densities that we don't know how to deal with general relativity by itself. But the upshot is that at a finite time in the past, we suppose that the universe was itself a singularity, that every point in the universe was sort of singular or in one singularity. So that's called the Big Bang singularity. But it's actually one of the things that comes up a lot if you're a cosmologist like me and you talk to the public, is that when I talk about the Big Bang in cosmology, sort of with my colleagues or whatever, I'm not usually talking about the singularity. I'm usually talking about the hot Big Bang, which is just the sort of idea that in the past the universe was smaller and denser and hotter. And so that's something that you can observe with the cosmic microwave background, the leftover light from the Big Bang, from this hot Big Bang, not singularity, but hot Big Bang like fireball that we know that the universe must have been in at some point. And we can see evidence for that. And so knowing that the Big Bang happened in terms of everything was hotter and denser and smaller in the past and it's been expanding. That's totally observational cosmology at this point. But extrapolating back to the Big Bang singularity, to saying that the Big Bang being the expansion from a singular point to everything we have, that's kind of a different issue. And that's something that we can't observe directly because we can't get to that point observationally. We can't see back to the Big Bang singularity, if it was a singularity, if it did all come from a single point. There's sort of complicated things that might have happened between the hot Big Bang and the singularity, like something called inflation, where you had the universe expanding exponentially fast for a while that made the universe way, way bigger and way more stretched out. And there's ideas to think that might have happened to solve various problems in cosmology. So getting back to the Big Bang singularity is actually really difficult with the sort of observational tools because there are a couple of sort of observational issues with trying to get to that and theoretical issues with things like trying to have an understanding of quantum gravity to be able to deal with those extreme densities. So, the Big Bang singularity is something that we often talk about as a possibility, but it's not sort of as clear as the black hole singularity in terms of that has to have happened. Black hole singularities, I think, are much more inevitable.
But even there is a sort of an analogy with the black hole that when I say we see black holes, we never see past the event horizon. There's actually a theory that you can never have a naked singularity.
Yeah.
It's always cloaked by the event horizon, which shields it from view.
Except the Big Bang singularity, which isn't behind an event horizon.
Why can't you see past the event horizon?
Because no light can get out from there.
Oh, right.
So you to see something, you need a messenger to tell you what's happening, and all the messengers got crushed to the center.
Right. So could I ask more question about the Big Bang singularity versus the hot Big Bang?
Yeah.
So one is the hot Big Bang. I'm just trying to understand this. So the hot Big Bang is a thing that we can observe because there's still evidence of it, like physical evidence of it, right?
Yeah, we see the afterglow in what we call the cosmic microwave background.
And then the singularity Big Bang is basically number crunching that
It's just if you take the expansion that we can observe and sort of dial that back, you get to everything being at a single point.
Right.
And that's the Big Bang singularity.
But you think of those two things as totally separate?
Yeah, because you can mess around with early universe theories and not have a Big Bang singularity. Weird things could have happened beyond the point where we can do any observations because, it's within that sort of fireball time that we can't see past. Or it's in this sort of quantum gravity regime that we can't really deal with. There are a lot of ways to have it not have been an actual Big Bang singularity, but we know that the hot Big Bang happened because we see the light that's left over from it.
So everything Katie said is right. Before I say anything, we really don't know what happened before this observable epoch, and we can mess around with the models in ways that what I'm about to say isn't inevitable. But let me just tell you the canonically simplest model so that you'll get a sense that this Big Bang singularity is a little bit more inevitable than it sounds. You have to do some pretty heroic work to get rid of it. Yeah. So first off, it's inevitable because of gravitational collapse is what happens. So what I'm going to take you is a mirror image in time to our universe, but one played in reverse time, where everything's collapsing in on itself instead of expanding out. But before then, did you know that the universe is infinitely large?
Yeah, that's what everyone tells me, yes.
Okay. And did you know that the universe is infinitely regular? No matter where you go in it, even if I could teleport 100 trillion billion light years away in one direction, the density of matter and the composition of matter would be about the same as it is right here, give or take. If you average out the density of a cluster of galaxies, it's about...
You have to be bigger than a galaxy.
You have to be pretty big to talk about the scales. But on the scales that drive the dynamics of the expanding universe, no matter where you go, the density is about the same. It's called the Copernican principle, named after Copernicus, who was like, hey, there's nothing special about the Earth. It's not the center of the universe, right?
Can I just jump in real quick with a bit of pedantry?
Yeah, you don't like Copernicus?
So what we can do is talk about the observable universe, which is as far out as we can observe. And within that region, everything looks Copernican and, it all looks good. But we don't actually know that the universe is infinite. That's a good assumption, but we can't observe beyond the edge of the observable universe.
Of course.
And so...
Well, that's where the underverse is, according to Riddick.
Right. I mean, so, of course, everything Katie said is right. We might be in some weird, all sorts of more complicated things could be happening at larger scales. And, of course, modern physics is playing with different ideas to take into account. I'm just talking about the very simplest assumption, because the simplest assumption makes the math a lot simpler. And so these were the first ones introduced. It's the assumptions that everything else are based on, and also the assumptions that we're testing and playing with when we're building new theories.
Okay, good. Yeah.
Not wrong at all, Katie Mack. Anyway, assume she's wrong. Everywhere you go, it's the same. Of course, untestable, because I can't teleport 100 trillion billion light years in any direction. I can't see for myself that everything looks the same. But like I said, it's named after Copernicus for good cause. There's no reason to suggest that there's anything special about our particular patch of the universe. And certainly, every direction we look, things seem to look the same. And so it's an assumption people think are pretty good. That said, it is a crazy assumption. The universe is infinite, and everywhere you go, it has the same density. It's reasonable in its simplicity, but also extravagant in its assumption. Okay, so the universe is infinite. But what happens is, even though it's infinite, it can expand and contract. And the way we see it expanding and contracting isn't stuff moving away from each other. It is, if you zoom in really close. But in essence, the way you describe it expanding and contracting is in terms of density. So if the universe is expanding, even though it's infinitely large, the density decreases. Right. And if it's contracting, its density increases.
Yeah.
Okay? And this system, even though it's infinitely large, it still gravitates. It still has some gravitation to it. And you describe its gravitation using Einstein's theory of general relativity. And the deal is, so I want you to imagine this universe, it's full of stuff. Everywhere you go, it's the same. As it contracts, it's not contracting to a point. We're just talking about the density increasing. But since it's gravitating, it's exactly numerically like the inside of a black hole, all of the matter collapsing down to a point. If you imagine our universe collapsing down to a point, what happens is, the denser it gets, the stronger the force of gravity gets. The more inevitable the collapse gets. So it gets denser and denser, and it starts to increase the speed at which its density is increasing. Yeah. You get a runaway contraction. It gets denser. So even though until the very last moment mathematically, the universe is infinitely large, and it's not collapsing down on a point, it's just that the density skyrockets and becomes infinite. And of course, the moment the density becomes infinite, the math stops working. And we call that a big crunch singularity. And if you play it backwards, universe stays infinite, but it starts out infinitely dense, and then it starts expanding outwards. That's the Big Bang singularity.
Okay, say if we do a big crunch, right? If the universe eventually does a big crunch and collapses in on itself, maybe again or whatever.
Okay.
Right? Is there a reason why it would want to expand again?
Okay, so the devil's in the details.
Yeah.
And so what happens is, there might be physical effects that are too subtle for us to know about right now, that become very strong and very important when the universe is really, really, really dense and hot. It's kind of like the strong nuclear force and the weak nuclear forces only happen inside the atom. They don't happen outside. So there might be effects that only start to dominate when things get really, really dense. And what happens is, it might be that those effects act kind of like a spring. What happens is the density gets so strong that those effects start to play in, and those effects say, hey guys, we can't keep collapsing. We're running out of steam. And it's called a cosmological bounce. It causes everything to stop contracting, the density stops getting denser, and it starts to expand. Its density starts getting...
But that wouldn't happen with a black hole, though.
Well, nobody's sure.
But we see what looks astrophysically like black holes.
Yeah.
And they haven't bounced back into our universe, at least. The idea is maybe the center kind of pinches off into another universe, but that's totally beyond anything we can observe.
Yeah, these things happen inside black holes sometimes too, mathematically.
Now, a long time ago, I heard about one of the universe models being like a static universe or something, that there was no Big Bang, that the universe always just existed infinitely.
Well, that's what sort of Einstein tried to do when he was first coming up with GR, because that's sort of the picture people had about the universe, was it was sort of eternal. But then there's various paradoxes that arise if you think about the universe that way. And
we also discovered expansion. And so that made it clear that the universe is changing and not static.
It's funny. All of these things are coming together with that question because Einstein. You asked, could there be something? What could cause it to bounce? And Einstein introduced a term into his equations so that he could build a model of a universe that sets still. Because he was like, finally, things sit still. And then, like immediately after, Hubble put out a paper saying, "Oh, look, it looks like the universe is expanding." Einstein was right the first time. And he refers to that as his biggest blunder. But it turns out that this constant that he added into his equations, he did it by hand, but since then mathematicians have gone through his work and said, actually, maybe that term's reasonable to include in the equations, but it's possible that it can contribute to a universe that starts out collapsing and then bounces instead of big crunching. And it's also possible that you can make it, if it has a certain parameter, you can use it to cause the accelerating expansion, the dark energy that we see today. So it might be in there, but it's certainly not causing the universe to stand still. So Einstein might have been extra accidentally double right. Well, that was wonderful. Thank you, Jocelyn. Thank you, Katie. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. Jocelyn, you get a guava. And Katie, you get a watermelon.
Nom nom.
I'd like to thank my guest, Jesse Moynihan. Thanks, Jesse.
Yeah, thank you, man.
I hope you had fun.
Yeah, I did have fun.
All right. So listen, TIE Fighters, some of you might want to support our show financially, and that's understandable. We've got a couple ways to do it. If you want to support us, firstly, you can download a podcast app called Podiversity for the Android phone. It's a subscription for content-based app, kind of like Netflix, but for podcasts, and they only have a few podcasts, and they're all science podcasts, but they pay us cash money for downloading episodes. So if you get the app and listen to our show, cha-ching, we're in the money. Secondly, t-shirts. Go to our show at the TIE-Fi website and buy yourself a sweet shirt. Some of them were designed by brilliant designer Chelsea Anderson. Are the shirts kind of expensive? Yes, they are kind of. I'm sorry about that, but TIE-Fi gets a cut of each shirt sold, and they're really, really good quality, and they look fantastic. And Bethany bought one 2 years ago, and she's worn it every day since, well, at least twice a week since then, and it still hasn't worn out. The t-shirts are very high quality and very nice, so have a look at them. So that's it for the main part of today's show. If you keep listening past this, you'll hear some ridiculously fun conversations. Remember that if you like listening to scientists talk about science in their own words, you might want to listen to other shows on the Bracket Media Network. I'm talking about Astrarium about astronomy, Science Sort of about science and science culture, Weekly Weinersmith where they do science interviews, Technically Speaking where they talk about engineering. The intro song for the show is by Ted Leo and the Pharmacist, and the end song is by John Vanderslice. Until next time, my friends, good day, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
If you guys could help me out a little bit, there might be like a lot of leeway as to like how popular culture understands the meaning of singularity, because there's like people talk a lot about the internet singularity, you know?
The technological singularity is that the idea that the rate of change of technological advancement by whatever measure is the rate of change is increasing in a way that it's going to go infinitely fast at some finite time in the future.
Yeah.
So that's the same idea that we were talking about, this idea that you're looking forward in time, something is basically going to blow up.
That's basically the point at which computers are replicating themselves and making themselves more advanced.
Yeah, that's when like computers start designing themselves and they're going to do it better than we can. And so past that, so originally, at the start of the show, I was like, singularities are kind of sometimes used in science language when we mean the boundary between where we will be able to understand to where we won't be able to understand what's going on. And in this sense, so once computers start designing themselves, who knows how fast they'll be able to advance. And then after that, they're probably going to all take care of us and we'll all live in computer paradise.
Or they'll do what they did. Did you see Her? Did you see that movie, Her?
Yeah.
I haven't seen it.
Isn't it like a guy making out with a monitor or something like that? He falls in love.
No, it's a phone. It's a phone.
He falls in love with his phone.
But no spoilers.
Yeah, and no spoilers. I'm sorry. But it has to do with what we're talking about, I think, where the computers advance beyond human production and intellectual modes.
Yeah.
In a general term, a singularity is when your ability to predict what's going on stops working. Right? Whatever model you're using just is breaking down at that point. Mm-hmm. So you need something else. Predict what the computer will do.
Does that have to do with that singularity principle, like how you're defining it? Because I think the word singularity gets thrown around a lot.
Yeah.
Does that understanding of that Big Bang singularity, does that apply to, I've done a little bit of reading about quantum physics or just on the toilet.
As one does.
Yeah.
That idea that one particle is in communication with another particle faster than the speed of light. So one particle on one side of the universe can affect another one.
So that's the idea of entanglement, which I don't think actually involves any singularities.
Oh, okay.
So that turns out just to be straight quantum physics. One thing is that even though the particles, they're entangled, so they talk to each other, there's no way to transmit information faster than the speed of light.
Okay.
So it's sort of consistent with our regular picture, even though it's really non-intuitive.
Do you see any potential use for the principle of quantum entanglement? Is there any...
Oh, we just did a show on this. Yeah, you can do all sorts of neat things with it for communication things. You can use it to come up with a way to encode messages that is completely secure. The short answer is when two people are trying to communicate to one another using a code, you have to get the code to the other person so they can decode what you're saying.
Right.
And the process of getting the code to the other person itself requires some security, right? Because somebody can stop and, beat up the person with the suitcase full of codes, and then they can hack into all your codes. So what they do is they entangle two particles, and then one person looks at the particle, and the way he looks at it will change how the other person's particle reads. So if one person looks at the particle and it's a particle pointing up, the other person's particle, because it's entangled, will be pointing down. And so there's this way, there's no information being transmitted, but there's a coherent sense of what's going on the other end, and it's not hackable. You can't intercept that. And so you can come up with a scheme for making one-time pads, it's called, in ways to encode information, so that you never actually have to go down the street with a list of numbers that somebody can beat you with a blackjack and steal
to get your
But
that's cool. Now, if someone offered you a chance to go into a spacesuit and cross the event horizon, would you do it?
No, that would be a really bad idea. So the reason that would be a really bad idea. I mean, for one thing, you could never write home and tell people about it, which would kind of suck. So it would be nobody would ever know what happened. But the other reason is because of something called spaghettification, which is the technical term for what happens when you have so much more gravity at your feet than at your head that your body is stretched out into spaghetti. And that would be really unpleasant.
It's like a really extreme form of tides.
Yeah.
The way the Earth gets tides on either side of it.
Yeah.
You would be totally stretched in an extreme way.
And so you would die before
encountering the singularity or getting to answer deep philosophical questions. You wouldn't get a chance to do that. You would just get torn apart.
It would still be pretty cool.
It would probably be pretty cool, but only for a while, and you couldn't tell anyone about how cool it was.
Okay, so Jupiter's gravity is less than Earth's?
Okay. So the question, when you ask how much the force of gravity is, you want to know how much it weighs and also how far you are from the center of it.
Right, that's the question. Like, because Jupiter's so big, but Jupiter is also much more massive than Earth.
Yeah, so it depends on where you're standing.
So Jupiter has about twice the surface gravity of Earth.
Okay.
So it's just the way that the size and the mass balance out. It's like, I don't know, it's way, way, way more massive, like I think hundreds of times or something.
Yeah.
But because it's so much bigger, you only get twice the gravity on the surface.
Okay.
And there's no surface to Jupiter.
Well, yeah.
Yeah, it's just like, it's not, that's why I was asking, because it's not dense, right? It's just...
Yeah, it's like gas.
It's like gas.
Yeah, I mean, there's a difference between sort of density and compactness that's a little bit subtle with that, I guess, because some black holes, if you measure them by, the size of the event horizon and the amount of mass in them, they're not that dense on average.
Mm-hmm.
But something becomes a black hole when it's got more mass within its Schwarzschild radius, which is the radius of the event horizon, than a certain limit. So it's the compactness as defined by kind of the amount of mass within a certain radius that's defined based on its mass, rather than density per se.
Right. Like if you look at, say, the supermassive black hole at the center of our galaxy.
Mm-hmm.
So what's the mass of that?
It's about a million solar masses. It's on order of a million solar masses. I don't remember the number exactly.
That's at the very center of our galaxy is a huge black hole?
Yep.
I didn't know that.
Yeah.
Does that make you feel a little bit more doomed?
I don't know.
but no, the other thing that we've talked about is that away from the black hole, it just behaves like a mass like anything else. Like if we took the sun away and instantaneously put in a solar mass black hole, same mass, Earth would just go around in its normal orbit.
Right.
Yeah. So I mean, we'd all die, obviously, because we didn't have the sun anymore, but we wouldn't be sucked in or anything.
The reason that the black holes are so sucky isn't that their force of gravity is really big itself. It's that you can access regions of the space where the gravity is really, really strong that would otherwise be occupied by the star.
Yeah. They only suck when you're inside the horizon.
Yeah, they only suck when you get too close.
But it's at the center of the galaxy, so our solar system is being affected by it. It's like rotating around it, right?
We're rotating around because of all the mass between us and the center of the galaxy, not just the black hole. But
yeah, it's cumulative.
But the black hole is sort of the point around which all of the mass in the galaxy is rotating.
I see. So in our daily life, right?
Yeah.
You exist on the planet, right? You're walking around and you learn the violin or whatever.
Uh-huh.
And everything that you're interacting with exists, like makes sense within our idea, our common idea of time, Like everything that we do is, I wake up at 9. If I drop a ball, it's going to fall on the ground.
Mm-hmm.
It's not going to fall on the ground first, and then I'm going to drop the ball. You know what I mean?
Yeah.
I'm not going to be able to drop a ball into... So why do you think that something physical exists that's so outside of our common experience? Why do you think that in order to explain something we observe, our black hole observations, it has to be so abstract?
I mean, I think that the big difference is that our daily lives exist in a regime where space-time is like reasonably well behaved. So we can think of space-time as being, really fairly boring and flat. And it's just that around black holes, or inside black holes, space-time gets really, really warped and really messed up. And so because space and time are inextricably entwined in our ideas about general relativity and stuff, and special relativity, then you get these really freaky effects where space and time become really complicated. And the way that things happen and the way that, space and time are affecting each other change a lot in those regimes. And so it's because we're on a planet, and so our space-time is curved in the sense that we're in a gravitational field. But it's a pretty mild curvature, and so it doesn't create, sort of screwy effects.
We see hints of the whole space-time curvature thing in our day-to-day lives, right? Your GPS needs to account for the curvature of space-time around the Earth to get the timing right with the satellites.
And it has to account for the fact that time moves more slowly when you're moving really quickly. That's a special relativistic effect. It has to take that into account as well.
Oh,
and if you look past the sun when there's an eclipse, you see the positions of the stars behind the sun move a little bit because the sun is bending their paths. So our day-to-day lives, we don't really feel these things, but we've been able to measure all sorts of little things, like the orbit of Mercury kind of loops around in a faster way than it would without space-time curvature. So you sort of see all these things, and then you just extrapolate and you say, wow, this weird stuff exists in reality.
Yeah.
And when Einstein originally proposed the theory, like, people used these singularities as evidence that it was a bad theory.
Mm-hmm.
But it turns out that actually it's still the best description that we have, and that the singularities, we do observe their effects. We observe stars orbiting the black hole at the center of our galaxy. We observe hot gas falling into other black holes. So it's this weird abstract thing that has physical consequences.
Right. Can you imagine like a civilization that existed where space-time was more, like, less consistent or less...
Well, I was going to say there's a book by Greg Egan called The Clockwork Rocket about a universe where light has a different speed and things behave differently.
Oh, okay.
So, I mean, people do imagine, like, what if this behaved differently? But this idea of consistency, we're pretty sure that everything should fit together in the end of things.
I mean, by the time you're in a region of space-time that's curved enough to give you sort of noticeably freaky time effects, the gravitational field is so high, you're not going to be able to do a whole lot.
Could you imagine like a life form exist? I mean, this is like sci-fi, but a life form existing within a heavily curved inside that isn't affected by the massive gravity of a black hole? So there could be like a planet inside a black hole.
We don't know anything that's not affected by gravity.
I mean, everything exists within space-time, and everything is affected by space-time. Light doesn't have mass the way we think of it, but light travels through space-time, and the path of light is bent by the bending of space-time, and so really everything has to follow those rules.
Did you see that movie, The Black Hole?
Yeah. I love that movie.
I didn't see it.
I haven't seen it.
It came out when we were like one. It was like 1979, right?
Yeah, it's a Disney movie.
Yeah, with the robots.
Yeah.
And they fall into the black hole at the end. And it's really trippy.
They built a ship that could withstand the crush of the gravity of a black hole.
Yeah. So if in real life, if they tried that, the ship might be able to survive longer than the people inside it, because it would crush the people inside it just as well.
Oh,
it would spaghettify people.
So it's actually interesting.
So if you saw, say, gas getting sucked towards a black hole, right?
Yeah.
And you saw it reach not quite yet the event horizon, but then you see it cross the threshold, right? I understand that it would disappear. You wouldn't see it anymore, right?
Yeah.
But that's because it just has entered into a zone with no light.
We don't really see it cross the event horizon. We would kind of see it freeze on the event horizon and fade away, because once it gets to the event horizon, whatever light it's producing won't get to us. It'll go into the black hole. So let's say that you're shining a flashlight out from inside the black hole. The light from that flashlight will turn around and come back to you if you're inside the event horizon.
It will never reach the person on the outside observing.
Yeah. Mm-hmm. Yeah. And so if you're right on the event horizon, then the light from that flashlight kind of stays at the event horizon surface. And if you're outside the event horizon, the light from that flashlight can get out, but it'll be shifted to the red part of the spectrum, which is another
it'll be all stretched out.
It'll be all stretched out, and it'll take a really long time.
But that wouldn't happen if there was a big crunch.
Well, actually, we should say that our observations of the universe suggest that it's not going to crunch back down. It's actually accelerating to get bigger faster.
Oh, okay.
Yeah, so there's different kinds of big crunch kind of things as well. I mean, there's a model called the ekpyrotic universe where you have a Big Bang, Big Crunch cycle. And that it's a cyclic model, but you have sort of extra dimensional things happening, and you do get this expansion that we see now, but then you're collapsing in a different dimension also, and then you get the bounce happening. So you can do weird stuff with other dimensions and still get Big Bang, Big Crunch kind of things. But basically, the classical idea of a big crunch where the universe gets more and more dense and collapses into a singularity. That's, as far as we can tell, not going to happen in our universe, because we have something going on now where the universe is expanding and it's accelerating in its expansion, and that's due to something we call dark energy, and we have no idea what that is. But whatever dark energy is, it's causing the expansion to go faster. It's kind of pushing everything out. Mm-hmm. And so what we think is going to happen in the distant future is that everything's going to get more and more spaced out. Everything's going to get less and less dense. And the universe is going to sort of become more empty according to what we can see. And, the stars will die out and everything will get really cold and dark and and lonely, and it'll be extremely depressing.
Yeah, so depressing.
What do you... There's no reason to believe that, according to Copernicus, there's no reason to believe that it would be any different anywhere else. You know what I mean? And that made me think about that. That made me think about that story of Flatland and, the two-dimensional beings interacting with three-dimensional beings interacting with four-dimensional beings, and that our methods of observation are limited in our own way until we find some new way of observing.
Oh, yeah, indeed. In fact, there are models of the universe that have more than 3 spatial dimensions. There are models for universal acceleration, expansion, dynamics of the universe that take into account the possibility of larger geometries beyond the one which our universe exists on. The Copernican assumption is audacious in some ways and entirely reasonable in other ways.
Right, but it's a good place to start.
Yeah, that's right. That's the idea.
So you can have the sort of the base level of Copernicus, which is we're not special, without also saying that, and we see everything about what's in our neighborhood.
Yeah.
Right, sure. Okay.
But yeah, but if there were 4 dimensions, if there were 6 spatial dimensions, you'd say, well, why are we stuck on 3 dimensions? What's special about those 3 dimensions? Yeah. So it's, I mean, at some point in time, it just becomes philosophy of science stuff where you're like, you can't assume that you know everything. And it's just like, yeah, but the math works better this way.
Yeah.
So, you do what you can in the short time you have in front of the chalkboard.
Sure. Right. And you were saying that the way we measure expansion is through the density and not through distance, right?
Yeah.
Well, I mean, we measure
yeah. Hold on. Yeah. So in the model, it's preferable to talk about density instead of distance. But when we observe it astronomically, we're looking at long distances and seeing how light changes over them.
We're seeing things become more distant.
Yeah.
It's kind of funny. We were talking before that you have to choose the coordinates, right? To describe things. And when you're talking about the universe, you can choose coordinates that sort of expand with the universe. Mm-hmm. Or you can have sort of coordinates that say fix and have the universe expanding against them.
From it, yeah.
So depending on what you mean by our lengths getting bigger. So like the distances between things are getting bigger, and you can think of it in different ways.
Because depending on where you're at, it'll seem different depending on where you're measuring from. Is that what's...
Well, we measure galaxies by their Doppler shift.
Okay.
And we can see that as the galaxies are all flying away from us.
Yeah.
Or we can see that as actually the light from the galaxies is getting stretched out by space expanding.
Right.
And it's the same thing.
But some of them are not getting further because we're like moving with some of them, right? Or
yeah, so the nearby ones are not moving farther away. But as you go farther out where the other galaxies are not affected by our gravitational field, or we're not affected by theirs, then those are all moving away from us.
Right.
It's like if you have a river, you can have little eddies and currents and things, but as a whole, things tend to be going in one direction.
Yeah. Is unified field a scientific term, or is that a New Age term?
It can be a scientific term.
Okay.
Yeah, I mean, there's things called grand unified field theories, or grand unified theories, usually abbreviated to GUT, grand unified theory. And it's the name for a kind of theory that unifies the forces of nature into like one major, one single a theory that includes all the forces. Because right now, I mean, we can unify certain forces pretty easily. So we can unify electricity and magnetism into electromagnetism, and that's all very easy. And you can unify electromagnetism and the weak force, electroweak unification, and that happens at high energies, high temperatures. Then you have to, when you want to unify electroweak and the strong force, that's where grand unified theories come in. And we think that happened in the early universe when everything was really, really dense. We think that there was a time when you had the GUT era. So when you had grand unification of those forces, and then bringing in gravity, that's sort of beyond grand unification. That's quantum gravity, and that's the next step that we really don't know how to do yet.
In what sense have you heard the phrase unified field?
Oh yeah, that gets thrown around in like New Age circles.
Are they like we're all connected with a unified field?
Yeah.
That's New Age stuff.
Oh yeah, that's bad. we don't like that.
It's not physically meaningful.
It's like I can see the indigo children through the unified field.
Right,
I mean, there's quantum field theory, and there's effective field theories, and there's grand unified theories, and those are all physically meaningful. But unified field is not physically meaningful, as far as I'm aware.
Okay, my question a lot of times is, out of that hot Big Bang, what made up the building block material of the universe is just that energy or whatever eventually separated itself into different.
It's separated into like electrons and neutrons and the things that we see day to day today.
Right. Yeah. I mean, that stuff is all still there, right? I mean, that stuff, the original building block materials is all still what it was when it first exploded, right?
No, it's like, it's stuff that sort of condensed out of that matter energy stuff that was the beginning. So it's like, you know how with stuff like particle accelerators, so like the Large Hadron Collider at CERN, what they do is they take two protons and they smash them together and create this really high density, high energy collision. And then particles come out of that, and they get all sorts of different particles. Even though the particles they put in were protons, which are made of quarks, they get lots of different kinds of particles out of it because they've recreated some of that primordial soup of just like energy density. And then lots of different kinds of particles can condense out of that. And that's kind of what happened in the early universe, is that you had this energy density and particles came out of that.
I see.
The word condensation is actually delightfully vivid. It's kind of like how water condenses. Like, so if you have an enclosed chamber, it's got water in it, and you heat it up to the degree that water can't stably exist as liquid. What happens is water droplets can come into being, but because everything's so violent inside your hot box, it'll turn back into vapor, right? Yeah. And then if you cool it, as it cools, suddenly there gets to be a point in time where water droplet might form, and it can stick around. Yeah. And so there are all these fields, electrons and quarks and photons, and they're all interacting when it's really, really hot. But as the universe cools, as it expands, as it becomes less dense, suddenly an electron can form and stick around in its current form. And
right. Well, why would that soup that you were talking about, why would it form discernible, tangible objects?
So one of the things we can say is that, we see matter around us in all sorts of different forms that look very different. But if you go down to the smallest components, every electron looks like every other electron, and every proton looks like every other proton. They're identical. They don't have any differences between them.
Right.
And so when you have this sort of mass energy, the stuff that comes out just sort of by quantum probabilities are just this various spectrum of fundamental particles that can later arrange themselves into the things that you see in your day-to-day lives.
Why did they arrange themselves that way?
Each particle creation is kind of a probabilistic event, and sort of going into a lower energy state. So having this hot primordial soup is kind of higher energy, and then as the universe expands a little bit, it's less energy, and you create particles, and they're kind of an easier state for that energy to be in is the particles, and which particles are created is a quantum mechanical sort of probabilistic thing.
Mm-hmm.
Getting from there to what you see today, we don't really know the why, but we know how that happened. We know that, well, once there were enough electrons and protons and neutrons floating around, they started forming hydrogen, and once you had a cloud of hydrogen gas, some of them started just collapsing in on themselves and forming stars.
Wow.
And then once you have the structure of the universe, and we don't know all the details, but in general, we know how that turned into stars that exploded and formed other elements and formed new stars and formed disks that have planets. And then all the building blocks just sort of came together because of this dance of gravity and stars that are just fundamental physical things.
Yeah. That's cool.